Hello, I'm Esteban Quintero, and this is my control theory case study 3 for the UFFS. So original scenario, the UFFS is an unmanned free swimming submersible vehicle. Basically, there's an elevator that is deflected to cause pitch. This pitch creates force that causes it to rise or submerge. The control system is modeled in the block diagram as well. Here is a picture of the UFSS. So first we'll start with our block math. So we start off with this response, then we move this K1 over. We end up with K1 and 1 over K1 here because this K2 is 0. This bottom part reduces, and we're left with that single open loop transfer function with unity feedback. Because of my birthday, I end up with that overshoot, which I solved to get a zeta of 0.417. So here's the uncompensated system. We have a rise time, or a peak time of 6.51 seconds, rise time of 4 seconds, settling time of 18 seconds. And I end up getting a K based off my dampening ratio of 3.81. Also, we know that we have a valid second order approximation because our third pole is already 5 sigma away with the same K. So first we want to reduce steady state error by 10. How do we do that? Do a lag compensator. It's used to reduce steady state error. It provides phase lag to reduce it. It's a passive compensator, and poles and zeros are added near the origin to reduce effects on stability. Our K, as we find when we implement the system, reduces to 0.932 for our gain. So when we solve for steady state error, we have a type 0 system with a step input. I solve for a KP of 9.81 with that. And then I solve for our characteristic equation 1 over 1 plus KP. And then I put a steady state error of about 9.25%. As you can see here, we want to reduce that steady state error. So to get that, we divide our steady state error by 10 to reduce it by a factor of 10. And then we set it equal to KP, and we solve for a new KP of 107. Then we take our ratio of the old to new KP right here, and then we end up with this ratio, and then we select our pole and our 0 to get our GC of S equation right here. Using that, that's where I added the gain or the compensator to the system, which got me that gain with the same dampening ratio overshoot. And we also know that we have a valid second order approximation because our pole is significantly further away over 5 sigma, our third pole. So this is our lag compensated versus uncompensated. So we can see that our uncompensated and our compensated have different peak time, rise time, settling times. Our compensated takes significantly longer, but we can see that based off our transient response, we have a significantly lower steady state error. Even though it might be slower, we do get more accurate steady state as a result. Reducing steady state error to 0. This would be our PI compensator. The proportional and integral control eliminate steady state error. So based off our steady state equation, we have S plus our pole location over S, which makes it a type 1 system. Due to that, when we solve the steady state error, we end up with our 1 over 1 plus KP, which reduces to 1 over infinity when we solve for that, and that just gives us our 0 steady state error. Same overshoot is maintained. Our K reduces to 0.97, and we also have a pole, or a valid second order approximation because of our pole location for our third pole. Also, if we do want to improve, right here, if we do want to improve the response, the transient response to go faster, we would add like a lead compensator or a PD compensator as well. Here's comparisons of our uncompensated system to the PI compensated. As you can see, same deal. We have a more accurate steady state error, that goes directly to 0 rather than a really low value. And we also have a longer peak time, rise time, settling time. So our final decision comparison. So if I personally had to pick a compensator to use, I would go with the PI compensator. They are really comparable, but as you can see with the PI compensator, we have more favorable and slightly faster performance characteristics. We also have a steady state error of 0, which is more accurate. Even though the lag compensator has extremely low steady state error, we'd rather have none than a little bit always.